This is problem number 54 from chapter 4. It reads, a roller coaster reaches the top of the steepest hill with a speed of 6 kilometers per hour. Of course, that's going to be our initial velocity. It then descends the hill at an angle of, average angle of 45 degrees. That's theta, and it's 45 meters long. That's going to be our displacement, and we have a coefficient of friction, mu sub k, which is equal to 0.18. So they're asking for the final speed when it reaches the bottom of the hill. I've written some of our initial conditions here and made a bit of a sketch. We know that our initial velocity is 6 kilometers per hour. That's given to us in the problem, but we realize, hopefully, that those kilometers per hour units are non-standard. We need to convert to meters per second, 1.67. So we know that the speed at the top of the hill is 1.67 meters per second. Since we have some information about the angle of incline and the coefficient of friction, we know that we can solve for the acceleration. Once we know the acceleration, which is kind of an intermediate step, we'll then be able to figure out the final velocity, which is kind of step 2. So step 1 is essentially a dynamics problem. Dynamics problems always begin with a free body diagram. I'm going to draw the roller coaster descending down and to the right. When I draw in my forces, I'm going to get a perpendicular component or a y component of the weight vector. I'm going to get an x component of the weight vector going down and to the right. There's going to be a normal force of the track pushing up on the cart, and we're going to have a frictional force, which I'll call F sub Fr, going up the incline, opposing the direction of motion. When I write out my dynamics equations, the sum of the forces in the x direction is not equal to 0. I know that because the roller coaster is accelerated. That just simply means that the right-hand side of my dynamics equation is going to be not 0. And if I assume down the incline is positive and up the incline is negative, my dynamics equation then becomes mgx minus the frictional force is equal to F net. The sum of the forces in the y direction is equal to 0. I know this because the roller coaster is not accelerated vertically. I'm going to call up in the direction of the normal force positive, down the negative y-axis is in the direction of mgy is negative. This becomes the normal force minus mgy is equal to 0. I'm going to break each one of these terms into its constituent parts. mgx becomes mg sine theta. The frictional force becomes mu kinetic times the normal force, and F net becomes mass times acceleration. Over on the other hand, the normal force then becomes mg cosine theta, which then can be substituted over here in the x direction. So I'm going to substitute normal force over there. This then becomes mg sine theta minus mu kinetic times mg cosine theta, after I've made that substitution, is equal to mass times acceleration. We see that the masses cancel out, which is convenient, so a heavier car does not accelerate more than a lighter car. I can solve for the acceleration here by substituting in for g, 9.8 meters per second squared times the sine of 45 degrees minus mu kinetic, 0.18, times g, 9.8 meters per second, times the cosine of 45. And when I plug that into my calculator, I get an acceleration of 5.68 meters per second squared as my acceleration. If everything on the left-hand side is dynamics, then this has been reduced to a kinematics problem. And the second part of the problem is using a known acceleration to find a final velocity. I'm going to use Vf squared is equal to Vo squared plus 2a delta x. Final velocity becomes the square root of V naught squared plus 2a delta x. Now I'm ready to substitute in. My initial velocity is going to be 1.67 meters per second. I have to remember to square the whole term. Add to that 2 times my acceleration that I just found in the dynamics problem, 5.68 meters per second, times, and this gets a little awkward the way I formatted it, the displacement, 45 meters. When I put that through my calculator, I'm getting a final velocity of about 23 meters per second. If I needed to convert that to kilometers per hour, it would be about 82 kilometers per hour.